hope you are following. It's going to have a reaction medium. Now, in this reaction medium, we have gases present. Gases. This does quickly do a simple illustration here. Gases. Now, in this reaction medium here, or probably chamber, we observe that we have gases. And one thing we need to know about these gases is that they are made up of what? Molecules. They are made up of molecules. But you observe one thing in the gas, and that is the fact that the gases are moving in what they call random motion. This can move here, and so on and so forth. Different directions. And we observe one thing again, that the amount that are moving in different directions, they do not attract each other. And they do not what? Repel each other. And that is the basic of what they call kinetic molecular theory of gases. So gases are made of molecules and ions. The gases, they do not exert either attractive or repulsive forces. We also observe that this gas we're talking about today, that the volume of the gas is negligible. Now, for those that, for instance, that see where they are probably adding more air to a ball or maybe to a tire, you observe that when you are pumping this air to that vacuum, you observe the air is filling the empty space. What you observe again is that the air hits the wall of the container. That is, gases hit the wall of the container. And when it hits the wall of the container, you observe that the energy of these gases are what? Perfectly, I use that English very well here, perfectly elastic. And what do I mean by perfectly elastic? It means that there is no loss of energy. Please pay attention, because one area of question, good area of exam questions, is this place. You won't be tested every time on formulas, but tested on what they call word problems. How well do you understand the topic? That is one way you can be tested here. So no loss of energy tells us that this is a perfectly elastic reaction. So in a manner that heating themselves, not like human beings. If human beings will heat themselves, they will lose energy. But gases, they do not lose energy. So that's what they call perfectly elastic collision. Now, gases, like I said, we observe one about gas again, that if I increase the temperature of this reaction medium, let me increase it. Now, this reaction medium, as the temperature increase, the particles of the gas, they collide with one another. These gas, they collide with one another. And when they collide with one another, we observe that there's an increase in what we call kinetic energy. It increases. And let's recall, what is kinetic energy? And that is the energy of what? At motion. Energy at motion. So when these particles move, we observe that there are what they call an increase in what? Kinetic energy. So an increase in temperature will increase what? Kinetic energy. Please let's note that. So let's really look at some probably asked questions, and let's see how we can easily answer them, because we need to pay attention to how this question can be answered. Let's look at one of them there. Now, from the first question here, we're told that a gas that is confined in a rigid container, let's say this is a rigid container, is heated. Once you are heating a container, means you are increasing what? Temperature. So when you are seeing, when you are reading the question, please try to break the question to how you understand it. So, is heated. Which of the following statements is true? So for the option A, the kinetic energy of the gas particles will decrease. That is wrong. We said that earlier today, that as temperature increase, kinetic energy will increase. So that option A is wrong. B, the pressure will increase. Let's keep that one side. C, the density will decrease. D, the number of moles of gas will increase. Now, we don't know what. There are three things here in option B, C, D. Three things. Please pay attention. Three things. And what are the three things? Pressure, density, and number of moles. Many of us say, man, not really, how is it related to each other? Let's create a scenario. We call what we call we call what we call the ideal gas equation. That is what PV is equals to nRT. PV is equals to nRT. So if we make T, if we try to create a relationship here, let's say we have PV is equals to nRT. Let's make, since we are relating pressure, density, and how is the relationship between pressure and density? You can see that if let's say I want to do something like this, V over NR is equals to T over P. You can see clearly here that T is now that is inversely proportional to what? To pressure from this. And I look at the option there. What does this mean? Is that if I increase temperature, pressure will decrease. But the option B is saying that the pressure will increase. So that is wrong. That is wrong. That is wrong. That is wrong. So if I also let's look at PV equal to nRT. If I say PV over R is equal to NT, it means that N is directly proportional to what? Temperature. That means if temperature will increase, number of moles will increase. So we can say that option D is the best answer. But someone will say, how is it density? What of density? What of density? Let's create something today. Let's create something today. Let's consider the same equation we talked about, and that is what PV is equals to nRT. And recall, number of moles is equals to mass over molar mass. So PV is equals to M over big M, RT. And let's recall again that density is equals to mass over volume. So therefore, if I apply that illustration there, that means PM is equals to M over V, RT. And in doing that, you can see the relationship there. If M over V is there, you can see that M over V is what? Is density. So PM is equals to rho RT. So PM over R is equals to rho T. So you can say rho is proportional to what? To temperature. So let's look at it here. They said the density will decrease. You see that is wrong. Because if temperature should increase, we expect the same thing to happen to what? Density. So option C is of mole. So please, in your book, please do me this favor, please. In your book, PM is equals to rho RT. Please, circle this formula in your book. Very important formula. Please circle it in your notes. Same with this too. In this course, we are going to be, let's call this equation 1. And let's call this equation II. Please, I might be asking for them. Equation I, equation II. Number 2, equal masses of hydrogen and oxygen are placed in a tightly closed container. Which statement is true about the system? They say something there. Equal masses of the two different substances, equal mass of the two gases. Now, option A, there are more hydrogen molecules than oxygen molecules. That is wrong. Because they said equal masses. B, all of the molecules have the same velocity. C, both gases exert the same pressure on the walls of the container. Now, they say all the molecules have the same velocity. That is wrong. Now, we recall that for a gas, we look at how heavy, that is 100 grams of division. I'll talk about that there. Look at how gas, we observe that the higher the molecular weight of a gas, the lower the what? The velocity, or the lower the diffusion of such gas. So that is not a good answer. See, both gases exert the same pressure on the walls of the container. And C and D, all the molecules strike the walls with the same force. So now ask ourselves a good question. So if we are having two different substances, let's create another relationship from what we've learned today. If I say, PV is equals to nRT and N is equals to mass over molar mass. So let's say M of H2 plus M of O2 RT. Let's just do some little math over there. So both gases exert the same pressure on the wall of the container. We know that they will both exert the same pressure. So we know that they will both exert pressure. We know about that, but we don't know if they will exert the same pressure. That is something that we cannot tell, because now we know the depth of the gas, so that cannot be a right answer. So we will go with we've ruled out option A, option B, D. All the molecules strike the walls with the same force. It can't be the same force. What is force? It can't be the same force. So I think option C is the best answer here. Let's go to option C. Why? Because both gases exert the same pressure on the walls of the container. Yes. We learned that one of the molecular theory of gas, one of the assumptions there is an assumption. It might not be true, but one of the assumptions there is that molecules of gas hit the walls of the container. So they hit the walls of the container, is not with force, but we know that that pressure is involved there. So it's an assumption. So we can say that option C is what? Is correct. Option D can be ruled out. The next question there. A rigid metal tank contains helium gas. You can say the first three questions, they are awarded questions, and we have to rack our brain. Unlike the one we just click on formula and get the answer. Awarded problem questions. You take your time, you analyze the question, so you don't make a funny mistake. A rigid metal tank contains helium gas, which applies to some helium, is removed at constant temperature. Now, the volume of gas decreases, which applies to some helium is removed at constant temperature. I think the question, let's read that question. Hopefully we'll check to correct it and give that next class. The question is not complete. So we can look at the next question there. At 17 degrees Celsius. Now, questions like this, physical chemistry questions, you don't form units in your head. You don't form things in your head. You write down parameters. That is the basic things first. The first thing you first do is to write your parameter. Don't say, I know what I'm doing. Don't know what you are doing. Put your parameters down first. We are told that at 17 degrees Celsius, a temperature of 17 degrees Celsius, a sample of hydrogen gas occupies V1 is 125 centimeter cube. What will the volume be at T2 100 degrees Celsius if the pressure remains constant? Pressure remains constant. We recall, what rule is this? This is Charles' law. Charles' law. Why is it Charles' law? Because the volume of the sample of gas is directly proportional to temperature, provided that pressure remains constant. So if pressure is constant, K, constant, this is what Charles' law. And this also tells us about Boyle's law. And what is Boyle's law? That the pressure of sample of the gas is inversely proportional to the volume of the gas, provided that what temperature remains constant. So this is Charles' law. The reason why I give this question, normally we say, this guy, why is it very simple now? It's very simple now. I want to show us something here. That sometimes you need to be very, very smart in solving questions. Now, first of all, T1, let's convert to Kelvin. Let's convert it to Kelvin. How do you convert to Kelvin? Please follow me. Degree Kelvin is equal to degrees Celsius plus 273. Please don't joke with this formula. So doing that, I can add 273 to 100 degrees Celsius, and that is what? 373 Kelvin. Do the same for this. If I'm adding 17, if I'm adding 17 to 273, I will get 290 Kelvin. 290 Kelvin. That means let's observe something here. That T1 is 290 Kelvin, T2 is 373 Kelvin. Now, 290 Kelvin to 373 Kelvin is an increase in temperature. We can see clearly here that temperature increased from 290 Kelvin to 373 Kelvin. That means we expect the same thing for volume. So if volume is V1, if V1 is 125 centimeter cube, V2 must be greater than 125 centimeter cube and not less than 125 centimeter cube. So you look at your option, look at the options. Which of the options is less than 125 centimeter cube? You see an option like Z, just cancel that option. Why are you doing that? Because it increases what? Accuracy. It increases accuracy. You look at the option there, you can see it there. There's a trap there already. Option A and option B is out. A is 21 centimeter cube. B is 97 centimeter cube. So if A is 21, B is 97, we can see that they are less than 125 centimeter cube. That means they can never be the answer. Sometimes you can be very, very lucky. You cannot see that 3 options goes in that way. You have 1 option, they don't stop yourself. Just mark it as your answer because you understand the basics of everything. So, but now we have 2 options, 161 centimeter cube, D 735 centimeter cube. So we have to solve. You have to solve. You have to solve. So let's recall. How do you sometimes you might also forget the formula? Just forget the formula of Charleston. You can derive it. You can derive it. Let's do it together. So volume is directly proportional to what? To temperature. So V is equals to KT. V over T is equals to K. V1 over T1 is equals to V2 over T2. We are looking for V2 today. Making this formula, that will be V1 over T1 times T2 times T2. What is your V1 today? Your V1 is 125 times what is your T2? T2 is 373. And what is your T1? Your T1 is 290 Kelvin. So I have a calculator here. I hope you have yours. So that is 125 times 273 times 373 divided by 290. So I'm getting 160.78 Kelvin. So look at the option there. That is same thing as you say 161 centimeter cube. So that is option C. Final answer for option C. So you see, that means we are accurate. If you can rule out 2 options, we are left with C and D. You know, anyone we pick will be what? Will be very, very correct. Now, I hope you are following me. I have another question here again. A gas cube diffuses through a porous plug. This is a question that you cannot miss it in the exam. And most of the times in the exam, you see it as a theory question. For people running from such question, why running from such question? Understand the basis of the question. The rule about physical chemistry topics, and of course, is that you must know where the question is from. If you don't know where the question is from, then that is a problem. That is a big problem. So now, quickly, a gas cube diffuses through a porous plug at a rate of 1.43 centimeter cube per second. Please write your data. They say gas cube, CO2. These are the gases involved here. You can say this is 1, this is 2. So R1 is equals to 1.43 centimeter cube per second. Diffused through the plug at a, we are told that CO2 diffuses through the plug at a rate. So please note, CO2 diffuses at a rate of 0.43 centimeter cube per second. That's the molar mass of Q. Molar mass of Q. Molar mass of Q is the unknown. Please pay attention. Pay attention. Pay attention. I want to derive some formulas now, so please pay attention. Molecular mass of Q. Now, we recall something. The ground law of diffusion is state. What does it state? You can recall that it states that the rate of diffusion of a gas is inversely proportional to the square root of its vapor density. So you can say that that rate is inversely proportional to the what? The square root of vapor density. Vapor density of the gas. But now recall that molecular mass is equals to 2 times vapor density. Please, don't joke with this formula. Don't joke with this formula. Equal to 2 times vapor density. So if I input this molecular mass here and derive it, I'll get something like this. R1 over R2 is equals to square root of M2 over M1. Please, this formula, let's call it equation 3. equation 3, please, equation 3, let's note that. Now we have our data. Molecular mass of Q, we don't know it, but molecular mass of CO2, we can solve for it. The molar mass of carbon is 12. Molar mass of oxygen is, the atomic number of oxygen is 16. Atomic number of carbon is 12. So 12 plus 32, and I get 32, that is 16 times 2. And that is what? 44 grams per mole. 44 grams per mole. So we can solve, we have our data now. So it's easy for us to solve. So 1.43 over 0.43 is equals to the square root of 44 over mq. So 1.43, we now 1.43 over 0.43 all square. You are removing the square root, is equals to 44 over mq. So we can solve like this. Let's do the maths quickly. 1.43 divided by 0.43. That is 3.3255. But you can square it quickly. That is 11.05995 equals to 44 over mq. So mq will be equals to 44 over 11.0595. And let's quickly do that. So 44 divided by 11.0595, and that is 4 approximately. 4. That is 4 approximately. That is 4. We can say that the molar mass of Q is 4 grams per mole. Do you have the answer there? Let's check the options. Let's check the options. Let's check the options. 4 grams. Yes, option C. Option C. The 1.6 grams of the gas. 1.6 grams of the gas. Please write your data. Please. Don't joke with this. You see how I'm solving questions over and over again. Write your data. 1.6 grams of the gas. 1.6 grams of the gas occupies, okay. 1.6 grams of the gas occupies 1.2 dm3. So mass is equals to 1.6 grams. Occupies, volume is 1.2 dm3. What is the relative molecular mass? Molecular mass of gas is unknown. But we are told that the molar volume of the gas at RTP is 24 dm3 per mole. Now, this is a very funny question. So we can try to now look at it in a different angle. And what is that angle? Is that 1.6 grams of the gas occupies 1.2 dm3 as room temperature and pressure. What is the relative molecular mass of the gas? We don't know the relative molecular mass of the gas. But if you can recall, it's similar to a gas. I also had to put a question, but you can recall your relationship, molar relationship. Let's consider a gas, O2. You see that 32 grams of oxygen gas is equals to 22.4 dm3 of oxygen gas. Normally, naturally, this is what you do. This is what you do normally. You can recall your mole relationship. This is a relationship question. So some people are like, what is this guy? What is going on here? We don't know the gas. Now, let's say we don't know a gas. We don't know a gas now, for instance. But we know that the gas molar mass, let's say gas molar mass is X. So X gram will be equals to 22.4 dm3 of the gas at STP. That was to be the volume at STP. Now, we know that 1.6 grams of the gas occupies 1.2 dm3. So we need to know what will be the mass equals to 1.2 dm3. We can stay clear. Let's do a simple math. Some people will not be overthinking. What is going on? What is going on? This is how I can solve such questions. Sometimes you know all times you use your gas to recall what you did in your basic chemistry. So 1.6 times 22.4 1.2. That is 29.87 gram per mole. You are having the answer there. 29.87 gram per mole, which is approximately what, 30 gram per mole. We look at the options there. Oh, sorry, it's not 22.4, it's 24. It told us 24. Not 24. Sorry for that mistake. 24. 24. So if I change everything to 24, that's why our answer was looking somehow strange. Let's quickly do the math again. 16 times 24. 16 times 24 divided by 1.2. That is telling us is 320. 320. I think I'm putting the questions might be omitting something. 320 gram per mole. And the correct to such answer is can be no, I'll go with option D rather. I'll go with option D, but it's closest to what we are solving here. But let's see. Let's ask the question. Let's see if we can check the questions very, very, very. Or maybe the question is 16 times 2.4. Okay, it's 1.6 times 24. 1.6 times 24 divided by 1. Okay, yes, are correct. Sorry. So it was from my own side. It's correct. So it's 32 gram per mole. That is correct. 32 gram per mole. So there was a question I'm having here. The last question before the worded question. I want everybody to attempt that. That is our first question for today. To be a time we give everybody to get the answers. Like so let's try the question. Let's try the question. I would like us to try that question. That is like our class work. But before then, let's undo this last question. The circular following is not an assumption of the kinetic theory of gas. It's not an assumption. It's very clear. I don't just revise what we did last time. So all collision with particles in gas are perfectly elastic. Option C is correct. The diameter of the gas particles are negligible. Yes. Recall that we said that the volume of the gases are negligible. And the diameter contributes to the volume, so it's negligible too. A, but our forces exist between particles in the gas. You can say A is not a suitable answer. It's not a suitable answer. So B is also correct too. So I want everybody to quickly try question the question for that's the molar volume of nitrogen gas. So let's quickly attempt it. Let's quickly attempt. I'll give everybody 4 minutes. Just 4 minutes attempt it. Then I'll come back to do it together with everybody. Please attempt it. Yeah, now.
Yeah.
So everybody, I believe that we can just quickly do the correction. So I've just written the data, so we can go straight to the point. Now we said molar volume. Molar volume means volume per mole. Volume per mole. So it means that in the gas, the gas has 24 gm cube in 1 mole. So we can get the number of mole is 1 mole. Is 1 mole. So density. Now, what is your pressure? Pressure, if it is at STP, that means 1 atm. Molar mass of nitrogen gas. Nitrogen gas, that is N2, is what? 14 times 2. That is 28 gram per mole. That is times 28. Our R is 0.0821. Why are we using 0.0821? Because of unit. Because of unit. And what is the temperature today? The temperature at room temperature, that is 298 Kelvin. 298 Kelvin. So that is, let's do that. 28 divided by 0.0821 times 298. That is 1.14 gram per gm. Let's see if we can have the answer. We have the answer there. We are seeing 1.167. 24 gm cube. Oh, sorry. I think we are not. I think it's the closest answer. They are saying here that we are looking at, I think they want us to use this parameter. But we know our density is equals to mass over volume. Density is equals to mass over volume. So they're not giving us volume per mole. We don't have mass. Or is that what they want? We don't have mass. I believe this is the answer. That means there is no answer there. This is the correct answer. This is the correct answer. So with this, guys, good. 14 times 2, 28 gram per mole. I'm trying to, let's check if we are making a funny mistake here. Fourteen times 2. No, that's correct. 28 gram per mole is correct. This one is the volume. This is the volume. So I'm trying to cross check if there are anything that is omitted, that was omitted here. So I think there is no answer. The closest answer to that question is option B. Is option B. Is option B. Because even then, question we told that the nitrogen is 14, but it's nitrogen gas. So that is 14 times 2. Now, guys, I've sent practice questions. Please let's quickly go through them. Thanks for your time. I really appreciate it, guys. See you next week.